Today we're going to run some Si29 NMR, and we will do two different methods. One is probably a little better for quantitative measurements, that's the gate experiment, and the other is better for obtaining signal to noise much more rapidly than the other methods. So first thing we're going to do is just run the gate experiment. So we'll start gate by typing gate at the command prompt, give it a name. First query that it asks is, do you want to do gated decoupling or inverse gated? We want to do the inverse gated because Si29 has a negative gyromagnetic ratio. We're going to change the parameters on the screen to optimize this for the acquisition. How many scans do we want to do? Let's do other. We'll just do 8 scans so you can see. This is an important part. We want to give the silicon enough time to relax before we pulse it again. So I'm going to just choose 8 seconds for the relaxation delay. The data size is going to affect the data in several positive ways and possibly a negative way. Because it has a negative gyromagnetic ratio, we want the decoupler on as little as possible. With a 32K data size, the acquisition time is 3.28 seconds, so the decoupler is going to be on for that long. If we double the data size to 65K, the decoupler is going to be on for a much longer time, and that is actually going to adversely affect our data. So we're going to stick with 32K data. And then the flip angle, with a 60-degree pulse, you still get about 87% of the intensity of a 90-degree pulse, but 50% of the net magnetization vector is still aligned along the z-axis. So using a shorter pulse like that makes sense for a nucleus like this. This particular program will automatically shim the sample, just the Y shim, so it doesn't take too long. As it starts acquiring, this particular sample, Dow 704 diffusion pump oil, has 3 silicon but just 2 resonances. So we should see, there they are right away. The nice thing about this particular experiment again is that it's more quantitative than the next experiment that we'll do, and it will, let's turn off auto scaling, give us a chance to integrate these peaks and then compare that to the other experiment where we get a little bit better data, faster data, but definitely not quantitative when you run the other experiment. As this is coming in, this is actually saving the data to the hard drive after every scan. So if you don't know how many scans to do, you can set a large number and you can stop the acquisition at any time. So let's say that you don't know how many scans to do, so you set it up for 2,000, and maybe after 500 it's already adequate as far as signal to noise goes. You can just stop the experiment with the control K, and it will have saved the data to the hard drive after each scan anyways. Coming up on our 8th scan. By the way, it'd be nice to run this experiment again and maybe increase the relaxation delay to see if we get better integration values or whatnot. So you'll have to play with the parameters a little bit. The next thing we're going to do is run this X-Nucleus polarization transfer experiment. So you can just type XPT at the command prompt. I'll just click it right there. We'll give it a name. Just from previous experiments that I've done with this sample, I know that a good coupling constant is 13 Hertz, and I know that the best flip angle is 33 degrees, And for a relaxation delay, let's use the same 8 that we did with the last experiment to make it as equivalent as possible. These two experiments will take the same amount of time. So this is going to start running the XPT, and I think what we're going to see is that unlike the gate, which should have had a 2-to-1 ratio, this is going to have a different ratio. So this is not quantitative, but you're going to see that the signal to noise is going to go off the top of the, the peaks are going to go off the top of the screen. So the XPT is a great way to, if you have dilute samples especially, it's a great way to find out what's in your sample qualitatively. So you can kind of tell some information from the chemical shifts and whatnot. We could also run this coupled and get proton-silicon coupling information, which might be interesting. With the XPT, that would be easy to do. I think you can see already that the signal to noise of this particular experiment is leaps and bounds greater than the gate experiment, and almost incomparable to a standard 1D experiment that you would do for carbon. And again, this all revolves around the fact that silicon has a negative gyromagnetic ratio. All right, one more scan, and then we'll go process them, and I'll show you what the difference is. Experiment completed. We'll open the snap program. First we'll get the first one that we did, the gate. We'll do half a hertz line broadening and zero fill, Fourier transform, phase, ALDD. We'll put that in dual display mode, and then we'll call in the other experiment, the XPT, and we'll process this the same way. Baseline correct, exponential multiply, zero fill, Fourier transform, and then we'll bring our dual display back. So you can see in the same amount of time our signal to noise is through the roof. However, let's zoom in on these a little bit. If we try to integrate, do a quick baseline flatten. Try to get close here. Just set it to 1. So that's a 1-to-1 ratio. It should be a 2-to-1 ratio. The peak on the left should be twice the height, or twice the intensity of the peak on the right. So that's the difference for running the gated experiment or the X-Nucleus polarization transfer experiment for silicon 29.